All right. Last time I just went through examples of 2D kinematics. I want to say one more thing about acceleration in 2 dimensions. Give you a couple examples of that, and then we're going to move on to kinetics, talking about forces. And what is going on here? Oh, I bet it's that. Ugh. Okay, so I guess before I start, this week in lab is the lab exam. It's not a very high stakes endeavor. Each one is worth 3% of your grade, 3 1/3% of your grade. But we're doing that instead of a lab activity this week. If you want it, if you're scheduled to take it Monday or Wednesday and you'd rather take it the other day, feel free to just show up and take it when it works for you. It's not going to take very long. I think it'll probably take people between half an hour and 45 minutes for the most part, and then you're done for the day with lab. Any questions about that? So lab exam 1 is this week in lab. Yeah.
It's just the 3 packs that we've got.
That's all we've done so far, right? And so it's going to be questions like those, yes.
Okay, perfect.
And then spring break is next week. And then exam 2 in the class is not the week we get back from spring break, but the week after. Okay, so have that on your radar anyways. Anybody have any homework questions you'd like me to go over? Anything that's been confusing in the homework? Okay. Well, the first thing I want to talk about today is an intuitive understanding of acceleration in 2 dimensions. Okay, so I've mentioned that there's kind of a fundamental difference between acceleration in 1D and 2D. In 1D, acceleration means the object is changing speed. That's the only thing acceleration can do. If the object is speeding up, then the acceleration is in the same direction as the velocity. And if the object is slowing down, the acceleration is the opposite direction of the velocity. Okay, so for example, in 1D, if you have an object on a ramp, and this ball is rolling up the ramp, and slowing down, then the velocity is the direction of motion, the direction of the velocity. So the velocity would be this way. And slowing down means the acceleration is in the opposite direction of the velocity. So the acceleration is this way. Okay? And that's all that can happen in 1D. Anyone remember what the new thing is that acceleration can do in 2D that it can't do in 1D? Yeah.
Turn.
Exactly. Yep. So in 2D, this should say in 1D. So when we go to 2D, acceleration can do two things. The part of the acceleration that's parallel to the velocity determines whether the thing is changing speed. And the part of the acceleration that's perpendicular to the velocity determines turning. So the part of the acceleration that's perpendicular to the velocity makes the object turn. Well, if you have something moving along a straight line, all accelerations are parallel to the velocity. You know, like in 1D, all accelerations are parallel to the velocity. And so it makes sense that you can't have anything turning in 1D. Okay, but in 2D, that's not the case. So let me give you a set of steps for sort of visualizing, imagining the direction of the acceleration vector. So these are the steps for imagining the direction of the acceleration vector in 2D. Okay, the first step is draw the object in the real world and draw the path that the object is following. So draw the object and its path in the real world. So this isn't a position versus time graph or anything. So for example, you know, the object could be following a path like this, and this is the object at the instant that we care about. Okay, and let's say it's going, I don't know, let's say it's going that way along this path. Second, draw the velocity vector tangent to the path in the direction of motion. Okay, so I'll just copy this down below. Okay, so the velocity vector is in the direction the object is moving. A tangent, to draw a tangent, draw the two nearby points, draw the line that goes through it. So the tangent is something like that, and the direction it's moving is this way. Okay, so this is the velocity vector. That's the direction the object is moving at that instant. And if this object at this instant, if it's whatever is making it move along this path disappeared and no more forces acted on it, it would keep moving in that direction forever. Okay? Third, if the object is speeding up, draw a vector that I'm going to call A parallel. The part of the acceleration that's parallel to the velocity. Draw A parallel in the same direction as the velocity. And then on the other hand, if the object is slowing down, draw a parallel in the opposite direction of the velocity. Okay, so let's say that this object is slowing down at this instant. We said that the velocity is this way. If it's slowing down, the part of the acceleration that's parallel to the velocity is opposite, like this. Okay. Next, that's 3. Now draw what I'm going to call A perpendicular, the part of the acceleration that's perpendicular to the velocity in the direction the object is turning. Turning. One way to think about this, I mean, you can think about which way the object would have to turn its steering wheel to stay on the path that's drawn. You can also think if you fit a circle to the path at that instant that you care about, this line is always going to go toward the center of the circle. Okay, so that's what I'm going to write down. If you fit a circle to the path at the desired location, A perpendicular is toward the center of the circle. Okay, so for this one, if I fit a circle to the path at this instant, it would be on this side. Do you see that? Any questions about what I mean, fit a circle to it? And so that means that, A perpendicular always goes toward the center of that circle. So it would be like this. I'm sorry, I called this A perpendicular, but this should be A parallel. Yeah. So this is A perpendicular this way. And then the last step is the total acceleration is the sum of these two parts. It's the sum of the parallel part and the perpendicular part. Well, notice that we know the directions of A perpendicular and A parallel, but we don't know the magnitudes. In lab, we've talked about what you can say if you're adding up vectors where you know the directions, but you don't know the magnitudes. And so what this says is the acceleration vector is in the range of all the directions between A parallel and A perpendicular. Okay, so if this is A perpendicular, then the total acceleration has to be somewhere between those two parts. Okay, so for an object that's traveling along this path and slowing down, we've figured out that the acceleration is somewhere in that 90-degree range. Like an example might be like, maybe it's there. Okay, somewhere in that range of directions. Anybody have any questions about that? I'm going to just go through 3 examples so you can sort of see how this works. So first of all, let's think about an object that is turning. So let's say that this object is moving along a path like this. Let's say it's going this way. And let's say that this is the instant that we care about right here. Okay? But let's say that the speed is constant. And we want to know what's the direction of the acceleration. Well, if it's moving this way, the direction of the velocity is tangent to the path, so the velocity is like this. So at that instant, that's the direction the object's moving. Is it speeding up or slowing down? Or neither? Neither. So that says that there's not going to be any part of the acceleration that's parallel to the velocity, because the part that's parallel to the velocity changes the speed. Okay? And so I'm not going to put in any A parallel. Now, what about turning? if we fit a circle to this, it would be this way, right? And so the perpendicular part of the acceleration has to be toward the center of the circle, so it's this way. It has to be perpendicular to V, that has to be a 90-degree angle. Well, the total acceleration is A parallel plus A perpendicular. But in this case, A parallel is 0. And so the total acceleration then is just equal to A perpendicular. So if you have something that's turning but not changing speed, the acceleration has to be perpendicular to the velocity like this. So if you're in a car in a parking lot, like driving in a fast circle around a big parking lot, the acceleration that you're going through as you go through that turn is toward the center of this circular path. Okay. Any questions about that? Okay, now how about something that is changing speed but not turning? So let's think about an object moving along this path. Okay, so let's say it's here at this instant and it's moving up this path. It's not turning, so the path has to be a straight line, at least nearby to the instant we're considering. And let's say that it's speeding up. Well, the velocity is tangent to the path in the direction of motion, so the velocity is this way. It's speeding up, so is the parallel part of the acceleration in the same direction as velocity or the opposite direction? Same. So that is A parallel. It's not turning, so there's no perpendicular part of the acceleration. And that says that the total acceleration then is in the same direction as the parallel part. Okay. And notice that in the case where something isn't turning, we've just reduced this problem to a 1D motion because it's just moving along a line at that point. Okay. So everything, if something isn't turning, it works the same way that it does in 1D because it is 1D. Okay, one more. So let's think of an object in projectile motion. And I'm actually going to analyze this at 2 different points. So something in projectile motion goes through a parabolic path. That's not a great parabola. Okay. And I'm going to consider one instant when the object is on its way up and one instant when the object is on its way down. And let's figure out what we know about the acceleration based on this kind of analysis. Okay. If it's going, let's say it's going this way along that path. So first, when the object's on the way up, the velocity vector is tangent to the path in the direction of motion. When a projectile is on its way up like that, is it speeding up or slowing down? Slowing down, that's right. And so we're going to have a parallel part of the acceleration that's opposite the velocity. Okay. And then if you fit a circle to the object at this point, it would be on this side of the, based on the way that's curving, based on the way the curve is, the circle would lie over on this side. It would be bigger than that, but, and so the perpendicular part of the acceleration is this way. And so the total acceleration of the object at this instant has to be somewhere between those two directions. Okay? So the total acceleration is somewhere in there. Well, I mean, we've talked about free fall and projectile motion a lot. In projectile motion, what is we actually know the direction of the acceleration. What is it? Down. And so notice that a downward vector, so basically we've come up with two ways of thinking about the acceleration of something in free fall, and they agree with each other because that downward acceleration falls in the range we figured out it had to. You with me on that? Okay, now let's do it for the other one. So now it's on the way down. So the velocity is this way. On the way down, is it speeding up or slowing down? Speeding up. So A parallel is in the same direction as the velocity. If you fit a circle to this curve at that point and drew an arrow toward the center of the circle, you'd get that A perpendicular is this way. And so the total acceleration is somewhere between these two directions. Well, what do we know is the acceleration for something in projectile motion? Down, which falls in that range. So this is a way you can always use to visualize the direction of the acceleration for an object moving in 2D. Okay? And remember to consider the cases where, remember it also works if you are not changing speed or if you're not turning. One thing that's interesting about these two cases, the one where you're not changing speed and the one where you're not turning, is that since one of the two vectors that you're adding to get the total acceleration is 0, you actually know the exact direction of the acceleration anytime one of those two parts is 0. You don't have to think about it as a range. You know what I mean? So this one where it's only turning, we knew exactly the direction of the acceleration. And this one where it's only changing speed, we knew exactly the direction. It's only when you have both parts that you can only narrow it down to a range of 90 degrees. Okay? All right. So now we're moving on to the next topic. And this is 2D particle kinetics. Okay, well, kinematics and kinetics, it seems like a joke. Like, why do they have to make those two words so similar, you know? And I don't know the answer to that. But remember, kinematics is describing motion without causes. And so this is relationships between time, position, velocity, and acceleration. Kinetics is when you combine kinematics with the causes. And those causes are force and mass. So before we can start using the equations of kinetics, which are Newton's laws, we have to first define these two things, mass and force. Okay, so let me start with mass. This is the simpler of the two. And the definition that we're going to use for mass is a resistance, let's say a measure of an object's resistance to acceleration. Okay, so picture this scene from a football game. So you got this one player over here. He looks like the Stay Puft Marshmallow Man. Okay, and he collides with this other player. Okay. So what's going to happen when those two collide? The player on the left has a lot more mass, is a lot more resistant to acceleration, and so when they collide, the big player is basically going to keep moving as if they didn't even notice that this collision happened, and the player on the right is going to go flying. There's going to be a really big acceleration. Okay, this guy might not be able to run very far, but he definitely is very resistant to acceleration. The lighter guy has a low resistance to acceleration. A much smaller force can cause the same acceleration for this guy. In fact, a lot of times I think we tend to think of weight and mass meaning the same thing. And as long as the gravitational field is consistent, is always the same, they are very closely related. And so like you think of getting on a bathroom scale and think of it measuring your mass, and in a way it sort of does, even though really technically what it's measuring is how big the force is that the scale is applying to your foot. But for astronauts who are, say someone on a space station or in orbit, since there's no gravity, you can't use a bathroom scale, right? You actually can't use any kind of scale the way we're used to thinking of scales. You need gravity for that kind of thing. And it's really important that astronauts get an accurate measure of how their mass is changing over time, because there's a lot of loss of bone density and muscle mass and stuff like that. So they want to stay on top of that kind of stuff. So for somebody in a space station, how do they measure, their mass, how their mass is changing? You can't use gravity for it, so what they do instead is they take a machine that applies known forces, like vibrations, and they measure the acceleration that is caused by applying these forces to the person. And based on how much their body is accelerated by these forces, they can measure the changes in the body's resistance to acceleration, which is a measure of the person's mass. Okay. The SI units for mass are kilograms, so that's what we're going to always use. It may seem funny that it would be kilograms instead of grams, because why would you use the one that has a unit prefix? But that's just the way it is. And one important thing to remember about mass is that it's just a positive number. There's no such thing as mass having a certain direction. Okay, so remember, notice, mass is just a positive number. Without direction. Anybody have any questions about mass before I go on to force? This really is about all you have to remember for that. Okay, so now we have to define force, and that's going to be a little more complicated. So force is a vector, so that's different from mass. Force does have direction, and it measures the intensity and the direction of a push or pull on an object. Well, forces have to have directions, because if you push something this way, it moves that way. If you push something this way, it moves that way. Those are different, even if the magnitudes of those forces are the same. The units for force are really complicated looking. It is units of mass, times units of length divided by units of time squared. That's the most complicated unit we've seen so far. And because it's such an important idea, and because that's so complicated looking, we're going to give that its own name, just so it's easier to work with. Okay, the SI units for force are kilogram meters per second squared, and we give that the name Newton. And we'll just abbreviate it with a capital N. So 50 kilogram meters per second squared is the same thing as 50 newtons. In this class, there are only two ways forces will come up. There's only two ways forces will arise. The first one is weight. And weight is the force applied to an object by gravity. And the only other way that forces can be applied is by contact with another object. In fact, weight forces are sort of part of a category of force types, and it's not the only one. It includes like magnetic fields and not gravitational, magnetic fields, electric fields, and they're called field forces. And the idea of a field force is that if you know the location of an object, that's enough to specify the force that that field applies to it. So, but I'm not going to do any problems in this class with electrical fields or magnetic fields. So all you have to worry about is weight. Okay, so now that at least I've introduced these ideas of mass and force, the big equation for particle kinetics is Newton's second law. I'm going to abbreviate that N2L because I'm going to have to write that a lot. And Newton's second law says F net, that's the sum of all the forces acting on a body, is equal to the mass of that body times the acceleration of that body's center of mass. Okay, so let me, so F net is the sum of all forces acting on the chosen body M is the mass of the chosen body. And the acceleration of the center of mass, well, that's what it is. The acceleration vector of the center of mass. The acceleration vector of the chosen body's center of mass. Well, as long as we're dealing with particles, we're just assuming the object only exists at a single point, and that point is its center of mass. So I'm going to start leaving the center of mass off of this, but it's good to remember that that's what we're talking about. Okay, so now what we're going to have to do is we're going to have to start trying to figure out what we know about different types of forces. Okay, and there's two sort of categories of forces. There's the weight force, and then there's forces applied by things in contact with the object. So let's start out with the weight force and see what we can figure out about the force gravity applies to things. So this is the force applied to an object by gravity. And we can figure this out just by thinking about it if we think about an object that's in projectile motion. Okay, so imagine an object, and let's say it has a mass of 1 kilogram. So imagine a 1 kilogram object in projectile motion. So let's say this thing is flying through the air like this. And we'll use a coordinate system with the y-axis pointing up. What do we know about the acceleration of that object while it's in projectile motion?
Speeding up.
Yeah, we do know that. But actually, we know that the total acceleration, if you add it all up, is just a downward acceleration of 9.81, right? So we know that the acceleration vector is down at 9.81 meters per second squared. Or if we write it as components in that coordinate system, it's 0, negative 9.81. Okay. So now we can figure out the force gravity applies to this thing by putting it into Newton's second law. The only force acting on something in projectile motion is gravity. It's not touching anything. And so Newton's second law says the gravitational force is equal to 1 kilogram times this vector 0, negative 9.81. And so the gravitational force on this object is 0, negative 9.81 newtons. Okay, so based on this, we maybe think like, okay, well, this 1 kilogram object has a force applied by gravity that's down at 9.81 newtons. Maybe gravity applies 9.81 newtons down to everything. Okay, maybe. So now let's think of something with a different mass and see what happens. By the way, anybody know the relationship between pounds and kilograms? Do you know about how much a kilogram is? Yeah, it's like 2.2 pounds. The weird thing about it is pounds is a measure of force and kilograms is a measure of mass. So in order for those to have any connection to each other, you need to know how strong gravity is. And so on the surface of Earth, where we live, 2.2 pounds is a kilogram. But if you went to the moon, something that had a mass of 1 kilogram would have a much smaller weight in pounds associated with it. Okay. But yeah, it's on Earth, the stuff we're used to, a kilogram is 2 pounds, a little over 2 pounds. Okay, so now what about a 100 kilogram object in projectile motion? Well, Newton's second law says the gravitational force applied to this object is equal to the mass of 100 times what's the acceleration of a 100 kilogram object in projectile motion? 9.81 down. Everything's the same as long as air resistance is small. So we got 0, negative 9.81. And so this is equal to 0, 981 negative in newtons. Okay. So what we've seen is that we have two objects of two different masses, and gravity pulls on them with different strengths. Okay? The force that gravity applies to an object depends on its mass. It changes as the mass changes. Overall, what we would find is the force applied by gravity, applied to an object by gravity, is mg down where m is the object's mass and lowercase g is 9.81 meters per second squared. So let's think about how a bathroom scale works, okay? How is it that a bathroom scale can measure the force that gravity is applying to an object, Well, the way it works is this. Let's say that this person is standing on a scale And let's say that this person has a mass of 100 kilograms. And we want to know what's the force vector applied to the man by the scale. Okay, well, let's think about if the man isn't holding on to anything and there's no acceleration, the man's just standing there still. How many forces are applied to the man? What are the forces applied to the man? There's always the force of gravity. There's always the weight force. And then in this case, there's one other force acting on the man. What's that? Yeah, the force applied by the scale. Okay, so I'm going to write Newton's second law as, so we have a force vector applied by the scale. Then we have the weight force that's equal to 0 for x, negative 981 for y. That's the weight force. And these two forces add up to the mass of the man times the acceleration vector of the man. Well, what's the acceleration vector? He's just standing. There would be a downward acceleration vector if he was in free fall or whatever, but he's standing on this thing and he's not going anywhere. Remember, acceleration is just a measure of how quickly velocity is changing. So in this case, the velocity is 0 the whole time, so the acceleration is 0 the whole time. Okay? And so now I can just solve this like an algebra equation. F scale is equal to 100 times 0, 0. And then I'll subtract this weight force from both sides. So, minus 0, negative 981. And so that is 0, 0 plus 0, positive 981. Or just 0, 981 newtons. So what the scale can measure is the force that it's applying to the person. It can't directly measure anything about the weight that gravity applies to the person. But as long as the person has no acceleration, and as long as the only two forces acting on the person are the scale and gravity, the scale will tell you, how hard gravity is pulling. So that's the way a bathroom scale works. And if you want to weigh a little less, you can hold onto the towel rack. Like, remember Homer Simpson in that episode? When he, I don't know, that's a long time ago now. But if you put a third force in there, then this logic for the scale isn't going to work. If you pull up on something and put 100 pounds of force in your arms, then the scale's going to read a value that's much smaller than the force gravity is applying. Okay? Okay, I want to do one more similar example to this. I think this is kind of cool. I think you probably know that this happens, but I'm going to sort of show you how this works. So now let's say that this same person is on the bathroom scale, but the bathroom scale is on an elevator. okay? And the elevator is accelerating, let's say the elevator is accelerating down at 2 meters per second squared. What's the force the scale applies to the man? So think about being in an elevator during the, most of the time you're in an elevator and it's moving with a constant velocity, so there's no acceleration. But right at the start of the motion or right at the end of the motion, there is an acceleration as it goes from being moving to being at rest or vice versa. So when an elevator starts moving down, do you feel like there's less force on your feet or more force on your feet? When it's moving down, it's less, and when it's moving up, it's more. Okay? And I'm gonna do this calculation and you'll see how that works, okay? Why that works. So Newton's second law says the force applied by the scale plus the weight force, which is 0, negative 981, is equal to the mass of the man times his acceleration. If this elevator and everything in it is accelerating down at 2 meters per second squared, the acceleration is 0, negative 2. Okay? And so now I'll do the algebra. And we have, the mass is, we know the mass is 100. So the force applied by the scale is 100 times 0, negative 2, minus 0, negative 981. And so that's 0, negative 200. Plus 0, positive 981. And you get a force of 0, 781. So when the elevator isn't accelerating at all, the scale has to apply a force to the man of 981 newtons up. When the elevator is accelerating down, it only has to apply a force of 781 newtons up. Okay, and if you bring a scale to the elevator and try it, you'll see just for the short little time where the elevator is accelerating for a second or whatever, you'll see as you start going down, the weight measured on the scale go down briefly. And then as you get up to a constant speed, it'll go back up to the regular weight. And if you did the opposite thing and the elevator accelerated up, you'd see the weight go up briefly and then drop back down to 981. Well, not 981, but whatever your mass times acceleration is, Any questions about that? Okay, that's all for now. That felt like a lot today. But I'll give you a couple of problems to work on. And we'll just keep working through different types of force next time.